Imagine stepping onto an industrial site. You're walking past rows of high-voltage switchboards, and you have this literal superpower.
Oh, a superpower.
Yeah. Not, super strength or anything like that, but the ability to see the invisible forces that are tearing a system apart long before any physical damage actually happens.
Right. Okay.
Because you scan a wall and immediately detect the exact friction point, the hidden thermal stress, the single overloaded circuit that is just quietly heating up to catastrophic levels.
Honestly, it sounds like science fiction. You are basically describing X-ray vision for energy.
I know, right?
Hmm.
But for professionals in the electrical and industrial space, this is rapidly becoming the baseline standard.
It really is.
Okay, let's unpack this because today we are diving into the world of thermal imaging cameras. We've pulled together product specs, technical guides from Megger, and some really great field insights from Contractor Essentials.
It's a solid stack of sources.
Yeah, and the mission for this deep dive is to build the ultimate cheat sheet for you, the new contractor. We are going to explore the physics of how these cameras work, how they fundamentally shift workplace safety, how they interface with strict Australian standards, and then we'll dissect the Megger lineup to figure out which specific tool actually belongs in your kit.
And it's such an important topic because thermal imaging, well, it represents this massive paradigm shift in how professionals diagnose electrical and mechanical problems.
How so?
Well, historically, fault finding required physical contact, intrusive testing, and let's be honest, a fair amount of calculated guesswork. Now, the industry is transitioning into this era of visual, non-contact precision.
Okay, let me push back on that a little bit right out of the gate. Because electrical contractors have been using, multimeters, clamp meters, standard insulation testers for decades to find faults.
Sure, absolutely.
And they work perfectly well. So why should a contractor drop hundreds or even thousands of dollars to add a fragile, highly sensitive camera to a tool bag that is, frankly, already heavy enough?
Because traditional testing puts the technician directly inside the blast zone.
Oh, wow. Okay.
Yeah, undetected electrical faults are essentially ticking time bombs. When you rely solely on contact testing, like physically putting probes onto live terminals, you are interacting with systems that could experience a catastrophic arc flash at any moment.
Which is incredibly dangerous.
Exactly. A thermal camera changes that safety equation entirely. It detects infrared radiation from a safe distance. So you can scan an entire electrical panel from completely outside the arc flash boundary before you ever unscrew the dead front to touch a single wire.
That makes the safety aspect really hard to argue with.
Yeah.
You're assessing the risk before you even commit to the physical work.
Precisely. You're mitigating the hazard before you're exposed to it.
But how does the camera actually translate what it's seeing into something the contractor can, use on the job?
It all comes down to the fundamental physics of heat. Every object in the universe that is above absolute zero continuously emits infrared energy. Everything. Humans do, machinery does, and crucially, every wire and breaker in a facility does. The camera uses this specialized sensor called a microbolometer.
A micro what?
Microbolometer. Basically, when infrared radiation hits this sensor, it changes its electrical resistance. The camera's internal processor measures those minuscule changes in resistance and then translates them into a visual map, which is your thermal image.
So it's essentially assigning a color palette to temperature values.
Exactly.
Hotter areas show up as bright red or white, and cooler areas map to dark blues or blacks. It kind of reminds me of a doctor diagnosing a fever from across the room.
That's a great way to think about it.
You can instantly spot the patient with a temperature without touching them. But instead of an infection in a body, what does the infection look like in a switchboard? We all know resistance causes heat, but how subtle are the changes we were actually looking for?
Well, you are looking for what's called delta T. That's the temperature difference between components that are operating under similar loads.
Okay, delta T.
Got it. Right. So let's take a loose terminal connection as an example. When a screw backs out slightly, the contact surface area decreases, which increases the electrical resistance at that specific point.
And more resistance means more heat.
Yes. As the current pushes through that bottleneck, it generates excess heat. So on a thermal camera, that single terminal will glow intensely compared to the 3 identical terminals right next to it.
So it essentially paints a giant glowing bullseye on the problem.
It really does. And it's not just loose connections. You can also spot unbalanced loads where one electrical phase is carrying significantly more current and running visibly hotter.
Oh, that makes sense.
You can even identify failing internal components inside a circuit breaker before the mechanical trip mechanism actually actuates. Or you can see degraded insulation in a commercial building where cold air or heat is leaking out.
Here's where it gets really interesting to me. If we are seeing a failing circuit breaker heat up before it even trips, aren't we basically predicting the future of a facility's downtime?
Yes, that is the entire core of predictive maintenance. By catching these thermal anomalies early, facility managers can shift their whole operational model.
Moving away from the panicked emergency calls, I assume.
Exactly. They move away from emergency, high-risk, incredibly expensive reactive repairs and move towards scheduled, low-risk, controlled interventions.
So a contractor could, say, schedule a shutdown to tighten a loose buzz bar connection on a quiet Tuesday morning.
Precisely. And by doing that, they completely avoid a catastrophic meltdown and a total facility blackout on a Friday night when it's much harder to fix.
Okay, let's ground this in reality, though. Because knowing the theory is one thing, but stepping onto a scorching hot site in the middle of a Queensland summer with this sensitive diagnostic instrument introduces a whole new set of variables.
Oh, absolutely. The environment changes everything.
Right. So if we are relying on this visual map to make critical safety decisions, how do we know the map isn't just lying to us? Like, what are the blind spots?
Well, the camera is a fantastic diagnostic partner, but it absolutely requires human critical thinking. You can't just blindly trust the colors. The single most common rookie mistake is ignoring thermal equilibrium.
Thermal equilibrium. Okay, break that down for me.
Yeah, so contractors often power up a piece of equipment, point the camera at it immediately, see a normal temperature, and then just sign off on it as safe.
Wait, so I can't just point this at a machine the second I turn it on. Why does a 15-minute wait make such a massive difference?
Think about the physical properties of thermal mass and conduction. When a heavy piece of electrical or mechanical equipment is powered on, the internal components deep inside begin generating heat immediately.
Okay.
But it takes time for that thermal energy to actually conduct through the copper, the steel, the plastic casing, just to reach the outer surface where the camera's infrared sensor can detect it.
I see. So the fault is happening internally, but the surface just hasn't caught up yet.
Exactly. If you image a system 2 minutes after startup, it hasn't reached thermal equilibrium. A massive internal fault might look perfectly cool on the surface because the heat wave simply hasn't traveled to the outer layers yet.
That is terrifying.
It is. You really must wait 15 to 20 minutes under normal load conditions for the temperatures to stabilize before taking a reading. Otherwise, you are literally signing off on a dangerous fault, purely out of impatience.
That is such a critical trap to avoid. I mean, you could walk away thinking a site is perfectly compliant when it's actually melting down internally. What about the environment itself, though? We mentioned the Australian summer earlier.
Right, so the environment plays a massive role, specifically regarding something called solar loading. Let's say you are inspecting an outdoor switchboard, and the morning sun has been hitting the left side of that metal enclosure for 3 hours.
Well, the camera's going to show the left side as glowing hot.
It will, and an inexperienced user might look at that thermal gradient and declare, oh, there is a massive, dangerous, unbalanced load on the left side of the board, but it's just a false thermal signature caused by the sun.
Just a hot piece of metal baking in the sun.
Exactly. You also have to account for emissivity.
Emissivity.
Yeah. Highly reflective surfaces, like bare metal bus bars, they reflect the infrared radiation of the objects around them rather than emitting their own true temperature.
Meaning a shiny piece of metal might look cold because it's reflecting the cold sky, or hot because it's reflecting a nearby boiler, which completely masks its actual internal temperature.
Exactly. And that is the danger of using thermal imaging in isolation. It does not, and I can't stress this enough, it does not replace fundamental electrical knowledge.
You still need your other tools.
Yes. When you spot an anomaly like a glowing terminal or a suspicious heat signature, you don't just guess. You pull out your multimeter, your clamp meter, or your insulation tester to verify the electrical properties causing the heat.
The camera shows you where to look, but the traditional meters confirm what is actually happening.
Exactly. They are complementary tools.
So what does this all mean for the business side of things?
Yeah.
Because finding the fault and safely diagnosing it is really only half the job in the commercial space. The other half is proving you found it.
Right, which shifts the conversation straight into compliance and liability. And that is where the business side of contracting truly leans on thermal data. In Australia, the regulatory environment is extremely unforgiving.
Yeah, we are talking about the wiring rules in ASNZS 3000 and the strict design verification requirements for switchgear in ASNZS 61439. The Electrical Safety Code of Practice doesn't just suggest routine testing, right? It mandates verification.
It does.
But is a thermal image actually accepted as formal proof, or is it just like a nice visual aid to hand to the client?
Oh, it is far more than visual aid. It is objective, quantifiable evidence. When a modern thermal camera captures an image, it isn't just saving a simple color picture. It captures what's called a radiometric file.
Radio.
Yes, that means every single pixel in the image contains a specific temperature data point. Software can analyze that file later to show exact temperature gradients across the entire image.
So a thermal report is essentially a high-tech, unarguable receipt for your work.
That's a perfect way to put it.
It's the difference between a contractor vaguely writing inspected switchboard, temperature's normal, on an invoice, versus delivering a time-stamped radiometric PDF proving the equipment was operating within optimal limits at the exact moment of inspection.
Exactly. In today's regulatory landscape, risk must be demonstrable. You have to show your work. If an auditor walks into a facility, these comprehensive visual reports make regulatory compliance straightforward. But more importantly, they protect the contractor's own liability.
Because if a component catastrophically fails 6 months after your inspection due to some unforeseen external factor, the client's insurance company is absolutely going to look at the last person who touched it.
And if you only have a handwritten note, you are completely exposed. But if you have a radiometric thermal image proving the component was entirely fault-free during your maintenance window, your liability is heavily protected.
That peace of mind alone is worth the investment.
It is. Furthermore, it bridges the communication gap with clients. Telling a non-technical facility manager that they need to spend thousands of dollars replacing a degraded system based on a spreadsheet of voltage readings, that's a really difficult conversation.
Oh, I bet. They just see dollar signs and numbers they don't understand.
Right. But showing them a vivid, glowing red heat map of a system on the verge of catching fire, that justifies the invoice instantly. You are turning an invisible, abstract threat into a stark, visual reality.
Okay, the value proposition is totally clear here. Safety, diagnostic speed, bulletproof liability protection. But a new contractor standing in the tool shop still has to figure out how to navigate the hardware itself.
And there are a lot of options out there.
Let's dissect the Megger lineup and compare the options because the price variations are, well, they're dramatic to say the least.
They are, but Megger structures their lineup to match specific operational risks and environments. Choosing the wrong tool can either cripple your workflow or just drain your budget unnecessarily.
Let's start with the entry point, the Megger TC256. This one retails around $769, including GST. It's a rugged, handheld unit designed for standard field use. The specs list a thermal resolution of 256 by 192 pixels.
Which is solid for that price point.
Yeah. But the feature that stands out the most is the inclusion of 4 imaging modes, specifically something called multimodal image fusion, or MIF. How does that feature actually function in practice?
Multinodal image fusion is a critical diagnostic tool, especially at the entry-level price point. Because if you look at a pure infrared image of a complex, crowded switchboard, it can look like a blurry, abstract painting of glowing shapes.
Yeah, I've seen those. It's just a blob of red and yellow.
Exactly. It can be incredibly difficult to identify which specific wire or tiny terminal screw is actually generating the heat.
Because the infrared sensor doesn't see visual details, text, or color coding.
Yeah.
It only sees the heat.
Precisely. To solve this, the TC256 uses a standard visible light camera right next to the thermal sensor. The internal processor takes the high contrast edges and physical details from the visible light photograph and overlays them digitally onto the thermal heat map.
Oh, that's clever.
Yeah, it aligns the two fields of view so the contractor gets a hybrid image.
So you see the exact physical component, the serial number sticker, the color of the wire, all glowing with the precise heat data. That eliminates a massive amount of guesswork in complex panels.
It really does.
The TC256 also includes a laser pointer for targeting, a floodlight for dark mechanical rooms, and standard USB transfer to build those compliance reports. For under $800, that feels incredibly capable.
It's a workhorse.
But then we look at the next model up, the TC256P. The P stands for portable. It shares the exact same 256 by 192 resolution, the exact same imaging modes, but it costs around $1,204, including GST.
Right.
So as a business owner, why on earth would I spend over $400 more for the exact same internal sensor?
You are paying for the miniaturization and the workflow efficiency. The internal capability is largely identical, yes, but the form factor is radically different. The TC25M6P is completely pocket-sized and extremely lightweight.
Is a smaller plastic housing really worth a $400 premium, though?
It depends entirely on your daily environment. If you are doing routine commercial checks in an accessible building, the standard handheld TC25E6 is perfect. But consider the reality of industrial maintenance.
Okay, paint a picture for me.
You might be climbing scaffolds, crawling into confined roof spaces, navigating narrow catwalks, or moving rapidly between dozens of different jobs across a massive mining site.
Oh, I see. In those scenarios, having a bulky pistol grip camera swinging from a lanyard around your neck isn't just annoying, it's an active snagging hazard.
Exactly. Having a professional-grade thermal sensor that genuinely slips into a shirt pocket and can be deployed in 3 seconds alters how often the tool actually gets used.
That makes total sense. If it is cumbersome, technicians leave it in the truck.
Right, but if it is pocket-sized, they scan everything. That increase in diagnostic frequency pays for the $400 premium very quickly by catching more faults.
Okay, I can see the logic for specialized workflows, but that brings us to the real heavyweight of the lineup. The Megger TC640.
Ah, yes, the big one.
We jumped from about $1,200 for the Pocket model to approximately $16,384, including GST for the TC640. I have to play devil's advocate here. 16 grand is a down payment on a commercial work vehicle.
It is a lot of money, yes.
You are telling me a new contractor should even consider a $14,000 premium when the $800 model has the exact same image fusion modes.
The price jump is severe because the TC640 is an entirely different class of instrument. It's built for enterprise-level, high-risk infrastructure. The justification really comes down to 2 factors: spatial resolution and workflow integration.
Okay, break down the spatial resolution first. The specs say 640 by 480 pixels plus super resolution processing. How does that translate to the real world?
It is all about measuring small targets from extreme distances safely. When you're inspecting high-voltage transmission lines or utility substations, you cannot get close. You might be scanning a transformer from 50 meters away.
Which is a huge distance.
Yes. This introduces a concept called the spot size ratio.
Meaning how much physical area a single pixel in the camera covers at a certain distance.
Yes, exactly. With an entry-level 256 resolution camera at 50 meters, a single pixel might cover a 2-meter wide area.
Okay, so a pretty big chunk of real estate per pixel.
Right, so if a tiny 2-inch connection joint within that area is failing and glowing incredibly hot, the camera averages that intense heat with the freezing cold sky surrounding it inside that single pixel.
Oh, wow. So the average temperature of that pixel looks normal, and the massive fault is completely masked. You miss the failing joint entirely.
A critical failure goes completely undetected. The TC640's 640 by 480 sensor, combined with its interchangeable telephoto lenses, dramatically narrows that field of view. A single pixel might now perfectly cover only that 2-inch failing joint.
That is a massive difference in precision.
It is. Furthermore, the super-resolution software captures multiple rapid frames using the natural micro-movements of the user's hand to shift the sensor by subpixels. It then mathematically stitches those frames together to artificially multiply the thermal data density.
So it's really not just about taking a prettier picture. It is the mathematical difference between catching a multi-million-dollar substation failure and completely missing it because your sensor just couldn't resolve the heat signature from a safe distance.
Exactly. The cost of missing that fault is infinitely higher than the $16,000 price tag of the camera.
Okay, fair point. What was the second factor? You mentioned workflow.
Yes, the workflow. The TC640 is built on an open Android operating system.
How does an Android OS change a contractor's day-to-day operation?
Well, standard cameras require you to take the photos, drive all the way back to the office, plug in a USB cable, download the radiometric files, boot up proprietary desktop software, and then manually build the report.
Sounds like an administrative nightmare.
It's time-consuming. The TC640 has Wi-Fi, 4G capabilities, and allows for direct API integration with computerized maintenance management systems, or CMMS.
Meaning a technician can analyze the thermal data, pinpoint the delta T anomalies, build a fully compliant radiometric PDF report, and upload it directly to the client's cloud server while they're literally still standing in the substation.
Exactly. The administrative bottleneck is completely eliminated. When managing multi-million-dollar infrastructure, that level of immediate data transfer and pixel-perfect long-range accuracy are absolute operational necessities, not just luxury features.
It becomes very clear when you look at the scale of the risk. If you were doing commercial fit-outs, residential switchboards, and routine maintenance, the $800 TC256 provides all the safety, precision, and compliance reporting you need to run a highly professional operation. But if you secure a contract inspecting utility grids or heavy industrial manufacturing plants, you cannot rely on an entry-level sensor to keep you safe or accurate from 50 meters away. You have to scale the tool to the severity of the environment.
You match the diagnostic capability to the consequence of failure. That's the golden rule.
This has completely reframed how we should look at field tools. We set out to build a cheat sheet for new contractors, and we've uncovered a massive technological shift. We've seen how thermal imaging moves the industry from reactive, dangerous repairs to proactive, non-contact predictive maintenance.
It's a huge step forward.
We explored the physics of heat transfer, proving why patience for thermal equilibrium is just as vital as the camera itself. We examined how radiometric data transforms standard compliance reporting into bulletproof liability protection under Australian standards.
It protects the facility and the contractor.
And we've mapped out the mega lineup, from the rugged workflow of the TC256 and the confined space brilliance of the TC256P, all the way to the enterprise-level capability of the TC640.
It really is a remarkable evolution in how professionals interpret and interact with mechanical and electrical systems. And, looking at this technology leaves us with a truly fascinating underlying concept to think about.
Oh, yeah. Lay it on me.
Well, if we can now easily carry a relatively small device in our pockets that decodes the completely invisible heat patterns of the physical world, allowing us to literally see the future failures of a mechanical system before they happen, what other invisible operational metrics in our daily environments are just waiting for the right lens to be understood, optimized, and harnessed?
Man, that is a phenomenal thought to end on. It really highlights how much of our environment is still operating completely out of our sight. But for today, at least in the electrical realm, that invisibility is a thing of the past. Thank you for joining us on this exploration. Keep analyzing the world around you, keep asking questions, and we will see you on the next deep dive.